Hello, am I audible? Can you
Yes,
hear
sir.
me?
Yes, sir.
Okay, fine. So, good evening to all of you. I am Devapam. So, I'm the TA for this course, that is Basics of Inorganic Chemistry, taught by Professor Devapam Maiti from IIT Bombay. So, this is my second class today. Uh, Let me see how many are there. Okay, altogether eight, with the seven students. So, that's fine. We can start. Okay, somebody has questions. Yeah, Fasila.
Yes, sir.
Yeah, you can access the recorded videos. So we all TAs like upload these videos onto YouTube. Okay,
Okay, sir. Okay, okay.
you can access these videos later also. Not a problem. So let us start today. Okay, my screen is visible, right?
Yes, sir.
This is the class that will help you for the week two. So in week two we had altogether five lectures. So out of that, two lectures were for the remaining part of the previous week. That is your metal from the metallurgical parts to purify the metals from the ores. So that remaining part was covered in the first two lectures and another three lectures in this week. So this very important topic, that is coordination chemistry, or the chemistry of transition metals, that were introduced. So I'll try to give a gist of that and then I will discuss some of the questions. Okay. So starting with, okay, just a second. Starting from lecture 5. So in this class, what we taught was the high temperature chemical reaction, and one more topic was there, that is zone refinement. So I think this was covered in lecture 6. So this was about the first two lectures. Okay, so this part was remaining. I will briefly discuss this so that you can have some idea. So as you already know from the earlier week that in nature, all the metal ores are in the form of metallic oxides, right? So we learned about few techniques that are physical, or you can say mechanical and chemical method. Okay, and we also uh, discuss about some reduction methods, reduction method by substitution or by electrolytes. Okay, so apart from that, you can also use high temperature. So what is the main thing? So if you heat if you heat any of the metal oxides, ultimately will decompose it and you can get the pure metallic form. Okay, it can melt. The oxide can come out, but this process is highly energy intensive. Okay, so you want to heat it more than 3000 degrees Celsius. This is very high energy. Okay, and to get it industrial scale, it is much more difficult, right? So, okay, you are following, right? So I can change it. So what people actually use, they use high temperature along with some reductant. Okay, and mostly the reductant are used charcoal, or more precisely you can say carbon. Hmm. Why is that? Because carbon can take oxygen, okay, and it can form either carbon monoxide, carbon dioxide, like that. So if you take carbon monoxide, so all these processes, so your metal can also form metal oxides. All these processes has an energy requirement. Okay, so you have delta E, also you have delta H, delta S. So you know about E, H, S parameters. Okay, these are the state parameters. So this is enthalpy, this is entropy. Okay, this is energy. So as you all know, for a spontaneous process, delta G value must be always negative. What is delta G? G is called Gibbs free energy, as we all know. And this expression is given as, this is a very basic thing, delta G equal to delta H minus P delta S. Okay, so delta H comes from the thermodynamic part. Okay, it is different for both reactant as well as product. T is the temperature and S is the entropy. Delta S means the change in entropy. So suppose you are going from solid to liquid, then to gas. So as solid is more compact, your entropy will be much less. If you go to liquid, it will be much more dispersed, entropy will increase. Then when you go to gas, entropy will increase much more. So this is the direction where entropy increase. So this is one way of looking into it. So this is, if you consider the state, okay. So this is the entropy considered from the perspective of state. But if you consider as number, so from that time you can also have another view that is called statistical entropy. Okay, if your product is having much more number or equivalence compared to your reactants, then this will increase your statistical entropy. But we will not cover this part here. This is not of importance, this one. Okay. mostly we'll focus on the state, physical state, based entropy. Okay, so what happens? Most of the cases, metal are made are as oxides or as sulfides. But these sulfides cannot be reduced to metal in one step. So it has to go to oxide. Then we have to get to the metallic form. So how do we do it? There is one word that is called Bingham diagram. Maybe many of you have already know about it. Okay. So this is a diagram of delta G versus T. Okay. So suppose for a metal oxide, if you heat it, and okay, so I told that here we use charcoal. So what is the reason? Because charcoal will have a trend like this. So when you heat at some temperature, so this is your two process. And this is another one. Say this has some certain energy requirement. Okay. This also has some certain energy requirement. So when you heat it, after certain point, say this is T critical TC, it will follow this path. Okay. So if you mix metal with carbon and you start heating it after a certain point, you will get carbon monoxide and then you can get the pure metallic form. Okay, this is the utility of Illingham diagram. And mostly why we use this charcoal, because only carbon monoxide or for the carbon dioxide, the slope of the curve intersects the metal oxide curve. Okay, so that is why we cannot use hydrogen H2O couple, because in that case it also follows similar parallel path, so it will never intersect. Okay, and apart from that, zone refinement, so zone refinement is used to ultra purify metals. What is that? Suppose you have a metallic section, this is a metal rod, this is the core of the metal, and then you have a heating element okay, that is working along the cross section of your metal. This is the cross section, and it can move vertically. So you can fix it such a way that the motor can move vertically, and when it is melting, so at the end, so this is your metal. On one end, all the impurities will gather. Okay, so thing is that when you heat and cool successively, so when it is cooling down, the impurities shift to like one specific side. Okay, so then again you are heating and cooling the other part, so that is why it is shifting side by side to one specific part, and then you can cut it off and you can get ultra pure metal. Okay, and these are very much applied in electronics. Uh, Okay, this was all about the purification part left over, and some more techniques were discussed, like you can do distillation, like this thermal method we already discussed earlier, based on boiling point or decomposition point. Fusion method, okay, etc. So with that, we'll move to the next part, that is of most importance. Coordination chemistry, or chemistry of sun- chemistry of transition metals. The coordination chemistry is very important. Why? First of all, we discuss that coordination is a complex. Okay, it's not a compound. So there is a distinct difference between compound and complex. The complex is a certain entity where the atoms or ions are not free to access. Okay, unlike compounds. So we'll discuss it more when we discuss Warner theory. So in these course, basically you will be taught about Warner theory and stability of complexes. Then two theories that are complementary to each other. One is called valence bond theory. Actually, it's a long old theory, valence bond theory for normal compounds, but there is an extension to coordination compounds also. And then comes crystal field theory. And these two combines actually to give you LFT, that is called ligand field theory. So valence bond theory came first, and then to rectify its disadvantages or the defects, crystal field theory came. But after that, we could see that it is not uh, solely enough to describe all the properties of coordination complexes. And then we used to combine these two and get an theory called ligand field theory. Okay. So let us start with that. Warner discovered this coordination somewhere around 1910s. Okay, that is more than 100 years from today. So that time no facility was available. You don't have any characterization facility to know. You don't have any single crystal. All of this modern characterization facility you don't have that time. So what he observed is for a series of cobalt compounds like this, so all of these series of complexes show different colors. Okay, so he observed orange, for 6NH3, for 5NH3 it was purple, with one water it was red, and then 4NH3 compound showed green. And there was anomaly when he wanted to substitute these chloride atoms. So generally, as you can see in the structure, there are three chloride ions. So you can replace this. So if you use some Ag plus solution, you should get 3AgCl all the case. But it was not the case actually. So he get different number of equivalents for the silver chloride. So for 6NH3, he got three AgCl. For 5NH3, he got 2 AgCl. And then for 4NH3, he got only one AgCl equivalent. So there is one anomaly here, and then he recorded the conductivities. Especially molar conductivity. So that will give you the estimate of ions, the number of ions. So here also he got the same anomaly that was deviating from the expected result. Then he came up with this theory. So he assumed one model, and in that model there was, so he came up like this. So this was the complex that was COCl3 and 6NH3. He told that this all NH3 molecules come close to the metal and they form a coordinate bond. Okay, so this is like NH3, you have lone pair on the nitrogen atom. So this can donate to the cobalt center. Okay, and this way all 6 NH3 can come and it will form a hexaamine moiety that he termed as complex. Why complex? Because these NH3 molecules you cannot access them. They are sitting close to the metal center, and inside, so if you have 3 plus on the metal center to stabilize this 3 plus charge, you have Cl3 or 3Cl minus. Okay, this can stabilize it. So this was called primary valency that we can detect through all the measurements, and this was called secondary valency. So now when he proposed this model, after that all these anomaly measurements can be explained. So for this case, for 6NH3, you have 3Cl out of your coordination sphere. This is called coordination sphere. So this can be detectable, this can be replaced also. That is why you got 3 AgCl. For the other one, like for this case, cobalt Cl3, 5 NH3. This was staying like this way, 5 NH3 are coordinated and 1 Cl is inside. So if cobalt is 3 plus, already 1 Cl is inside, it will contribute -1. You have 2 plus on the whole, and then you have 2 Cl minus. So these are stabilized. So then if you replace it with Ag plus, you will get 2 AgCl. Right. So this way all these anomaly results could be explained. And from there, this theory came. Warner theory of coordination complexes. So at that point of time, this was very pioneer result. So that is why he got a Nobel at 1913. So this also tried to explain the color of the compounds, but not So effective. Okay. And we got an information on the geometry of the complexes. So you can have different geometry. I'm saying something. So we can have different kind of geometry. So depending on the coordination number. Coordination number means number of ligand, atom, or ion present inside coordination sphere. Okay. So as I told you, this is called the coordination sphere, and the number of say ligand like atom or ion, anything. Okay. So uh, the species can be species inside coordination sphere can be neutral, vectoric, or anionic. Okay. And number of species means number of coordination, or CN. If you have CN equal to 1, it will be like, so I will depict as L for the ligand. Okay. If you have Cn equal to 2, we can have like this. So this is called linear. This also can be called linear. Then if you go to more large coordination number, Cn3, you can have like this. So this forms a triangle at a plane. So that is why it is called triangular planar. You have Cn4. You can have two geometrical isomers. So these are called geometrical isomers because their molecular formula, everything is same, but they vary in the geometry. The typical tetrahedral structure. This is called square planar. This is called tetrahedral. CN5, you can have either of this type. So you have a square planar on the plane, and then you have one ligand that is on the top. This is called square pyramidal. And then we can have another one, three on the plane, and then two on the top and bottom. These are called axial ligands. These are called equatorial ligands. This will form a plane. It's called equatorial. These are called axial. And this geometry is called trigonal pyramidal. So at the plane, it is forming a triangle, and then you have two more ligands that are protruding top at the bottom. That is why it is called trigonal pyramidal. Then you can have CN6 CN6 you have two structures. One is called, so you have plane here. This is called octahedral. And another one you can have. So this will be like of the plane. This will be at the bottom. And again, this will be top of the plane. This will be bottom. So here you have a triangle between these three ligand. You have a triangle between these three ligand. And sometimes they can be staggered or sometimes they can be eclipsed. Okay. This is called trigonal prism structure. Although for the coordination number 6, mostly examples are in octahedral, but some of the systems can also take trigonal prism structure. Okay. If we have time, we will discuss a few systems that go to this special geometry. Then you have CN7. So after CN6, whatever more coordination numbers you can consider as, you have this octahedra. So in octahedra you have 6 faces. Okay, you have this one, the name of this. So it will have 6 face, 6 side, like that. So if you think of another ligand that is protruding out of one such faces, that will be called a capped. Okay, this is called a cap. So this will be called as capped octahedra. So there is one ligand or one point outside. This is called single cap octahedra, but monocapped. You can, it will be better monocap octahedra. And then if you have 8, then you can increase one more. Let's say you can then have one like this and one through this plane. So this is one plane. This ligand is capped through this plane, and the opposite plane here, another ligand is going to be capped opposite. This is called bicapped octahedra. Okay, so like that. So there are few more number also, CN9. Okay, like that. So mostly if you see this lanthanide atoms, which is lanthanide ions, which are very big in size, they actually go for the coordination number more than 6. Okay, so because they are bigger in size, they can accommodate more ligands. This was the preliminary idea, and then I already discussed what can be the type of ligands. This can be neutral, antibody, cationic also sometimes. Then a special type of ligand is there that is called chelating ligand. So these chelating ligands form a ring around the metal center that is called the chelate. Say this is your metal, and I am drawing one ligand. This one. So the nitrogen at these positions. Okay. This is called, this ligand is called tarpyridine. It is N3 donor because you have 3 nitrogen that can donate to the metal. So when it is binded to the metal, it will be like, so suppose you have an octahedral geometry. So 3 will be like this. Okay. This will be another end but different. This will be connected to here. Better I show with another color. Then we have this. Okay. So you can see it has formed. It has formed 1, 2, 3, 4, 5, 6, 7, 8. Okay. 8-membered ring it has formed, or not this. Just a second. Or you can consider this one. 1, 2, 3, 4, 5-membered rings around the metal center. So this is called 5-membered chelate ring. And when these chelate rings are formed, complex becomes stable. Okay, this is called the chelating effect because chelate, it restricts the movement of the ligand because one ligand is binded to one ligand is binded to 2 or 3 coordination directions. So that is why their free movement is blocked. So that decreases the entropy. Decreases conformational entropy. So that is why it is stabilized much more. Okay. So some type of uh, chelate ligands are a little bit better that we discuss in the next slide. Some examples will be ethylene diamine. This is most common. I think in class also this discussed. H2, CH2. Okay. Then you have lot of more things. So you can have, so this N can be like this also. Then you have something R group, then again something, and you have another R1 and then R2. So this can also work as a chelate. You can, apart from nitrogen, you can use oxygen. So oxalato group. Okay, it will be like, so this minus charge can going to the middle center, and then it can coordinate. Okay, these are the type of chelating ligands that are mostly used in the literature and people are also using. Then what are the types of isomerism? In coordination complexes, so mainly there are two types of isomer. One is called stereoisomer. Okay, another is called structural isomer. Stereoisomer can be optical or geometrical, and structural isomer can be of three types. It's a very basic. One is called linkage isomer. One is called hydrogen isomer, and one is called ionization isomer. So optical isomer is terms of their optical property. So if you pass plane polarized light, okay, the light that is oscillating in just one direction, okay, so it can rotate the plane of polarization of that specific incident light. So it can be either dextrorotatory or levorotatory. So depending on that, this optical isomerism term comes. Okay, and then you have geometrical isomers for specific kind of structural isomers, not structure, specific kind of geometry. Say you have this coordination number 4. Okay, you have square planar geometry. It is shown in the next slide. You have like this M, say, A2, B2. So how it can be formed. You can have this kind of geometry, or you can have on the opposite corners. Okay. So what is the differences in these two structures? You have a mirror plane here. Okay. That if you cut through this mirror plane, you will get the exact two halves. This is much more symmetric. So this is called trans, and this is called cis. Here, two similar atoms are present in the same side. Here, two similar ligands are present in the opposite side. Okay. So just like that, you have linkage isomers. Suppose you have a ligand that is cyanide, Cn minus. So this one negative charge stays on the carbon because nitrogen cannot hold negative charge. It is already is full valency is satisfied. Nitrogen can have maximum 3 bonds, right? So here, as nitrogen don't have the negative charge, but it has one lone pair. So this ligand is called ambidentate. Ambidentate. So denticity comes from the term denticity comes from the term number of donating atom. Okay, you can have different types. You can have monodentate, bidentate, tridentate, and so on and so forth. Monodentate is what? Where we have only one atom present, like this or like this. Okay. Bidentate means you have two atoms. So like ethylene diamine, you have NH2, then carbon, carbon, then NH2. You have two atom within one ligand system that can donate to the metal center. This is called bidentate. Tridentate I just showed you. This is called a tridentate ligand. Okay, it has three nitrogen atom in the same ligand that can bind to the metal center simultaneously. That is why it is called tridentate. So I can write it here, TARP. And apart from that, you have uh, pentadentate, more than that. So you can have metal cycles also, where you can see some of the structures are there. You can have a ring. Okay, so these are the density is much more. And ambidentate is where you can bind this ligand. You can bind through any of the atom. So carbon can also bind, nitrogen can also bind. So suppose you have a you have a coordination complex where you have a cyanide ligand connecting two atoms where N is also bind and carbon is also bind. So all the other valencies are fulfilled with some other ligand. Here also same thing. You have different ligands to satisfy the valencies. But then it can flip. So at some point it can flip. Okay, this is called cyanide clipping. So cyanide is a very interesting ligand. Those who are working in this field, so they can know the importance of cyanide ligand. So this is called flipping. And then it can change its dentate, like the atom that is associated with that metal center. So this is called linkage isomers, and similar thing can be observed with NO2. Okay, so you have both nitrogen and oxygen donor centers like that. Then you have hydration isomer. Hydration isomerism is the case where you have different number of crystallization solvents. Okay, so like that, suppose you have a complex MX6, then you have 2H2O. This 2H2O, it can vary according to condition. So you can have 3H2 also, okay, or 4. So it's H2O. So number of crystallization solvents differ. That is called hydration isomerism. Then you have ionization isomerism. Where we will have different, so you will have different ions satisfying primary valency. Say two systems are there, call it NH3 5 Br Cl2, okay, and then you have say cobalt, NH3. FCl, electron is only so one, and you have here. So in that case, you have different atoms or ions satisfying your primary valency, right? So from here you will get only this Cl minus plus the complex. Here we will get the Br minus plus the complex. But other things will be same. Your molecular formula as well as the charge on the metal ion will be the same. Okay, this is called the ionization isomerism. Let us go to the next part. Coordination compounds, sorry, complexes, specifically metal ions have variable oxidation states. Okay, say for iron, iron atomic number is 26. What is its configuration? It will be noble gas. Then you have 4s2 and 3d6. 3d6. Now, how many ways you can remove these electrons? You have 4s1, 3d6, then it will be Fe1, then 4s0, 3d6, add on 2, then 4s0, 3d5, you have add on 3, and so on and so forth. You can go up to full oxidation, 3d6, and that will be but all of the oxidation states are stable? No. Iron 1 we cannot see. It is very unstable. Somewhere very few complexes we can observe Fe1 state. Most stable is Fe2. Most stable. Okay. And this full oxidation is not possible. It cannot go through that because you have some limitations. When d electrons are filled, like this half filled or full filled, where this situation comes, so it cannot tend to more oxidation. So this is not possible. Iron 3 is also stable, not as iron 2, but it is stable, and it can go maximum to oxidation number 6. But this is too much tend to be reduced. So tend to be reduced very fast. So that is why is very powerful oxidized because it wants to be reduced very fast. Now let us move to another part, stability of complexes. So for the coordination complexes, one special rule of thumb was introduced in 1920s, that is called 18 electron rule. So you all know that 8 electron rule for S and P blocks. Okay, stable electron configuration. So this rule actually extends for coordination complexes also for the D block. And in the D, as you have 10 electrons coming from the D or D shells. So that is why total it is 18 electrons. So how do you find it? The rule is like all electrons from metal center plus electron coming from ligand. If this equals 18 electron, then it will be stable. So this has much more extension. So when we'll study some advanced courses, you can learn about clusters. Clusters is nothing but multimetallic structures, okay, where the type of structures, say octahedra I have discussed, say two octahedra are joined, okay, like this. So here you have a ligand that is shared between two octahedra. This is one. So it can be edge shared, it can be face shared. Okay, it can be shared by many ways. That thing will come later. That is not a point of discussion for the course. So we'll only focus for mononuclear complexes. Okay. Now, how do you calculate this? So any general rule is that any neutral ligand you can consider as two electrons. Neutral ligand may be amines, water, okay, all that have lone pairs, right? Or you can have some ligand that is having again nitrogen, so like that. If you have any anionic ligand, then you could consider 1 electron. You have like this, OSC, any halide, X minus, C8 minus, can consider like that. And then for metal, consider D electrons. So let us solve for one case. Say nickel carbonyl. Okay, nickel is D8 system. Hmm. So this is 4s2 3d8. Total is 10 electrons. 10 electrons, and you have 4 carbonyl. Okay, so 4 into 2 is 8 electrons. So altogether you have 18 electrons. Let us solve for another one. So FeCN6 4 minus. Altogether there is 4 minus. Cn is each 1 minus. Then what will be the oxidation state of iron? It is iron 2. 82 plus. Okay, so X minus 6 equal to minus 4, then X equal to 6, 6 minus 4, that is 2 oxidation state. Okay. For iron 2, we have the following electron configuration, that is 4s0 3d6. Okay. So now check cyanide. So here one more thing you have to remember. So there is two way to count electrons. One is called neutral method, and one is called oxidation state method. Okay. So in neutral method, you consider as neutral charges, for metal and ligand. Then altogether you take the charge outside. But in oxidation state method, you only consider the electron in appropriate oxidation, or more recently charge state. Okay, so I will show by this example to be clear to you. P Suppose you claim 6 electrons for this one, and cyanide if you take 2 into 6, that will come 12. So this will be total 18 electron. And then how can we get by other method? You take this one as 10. So this 2, sorry, plus will be better, I think, if you consider like this one. So what can you use for the moment? You can consider oxidation state, and then the number of electrons you can take for 2 plus, that is 6, and for each CN you can consider as 2, then it will be 12, 12 plus 6 will be 18. So that will be a stable configuration. Okay, and then two theories. Two theories were introduced. One is your valence bond theory, and then came the crystal field theory. So we'll first discuss briefly about valence bond, and then we'll go to the crystal field theory. So at 90s, Jean Lewis first came up with this valence bond theory, and here we considered there is a covalent bonding. This was all at the stage where this coordination chemistry was growing. So they thought it was all covalent bonding between ligand. So what were the assumptions? Ligand forms the covalent bond. Metal ligand always should have lone pairs. Okay, and then as ligand is donating, there must be one orbital in the metal that can accept that electrons. So empty orbitals are given. Okay, and what type of orbitals from the ligand are used for this bonding? It will be hybrid orbital. So the concept of hybrid orbitals was introduced in this theory. So that is why it would have, say, it would have sp2 or sp3 hybrid orbitals interacting with d orbital. So how does they interact? Suppose, say for this example, for cobalt 3 plus, cobalt 3 plus is 3d6, 4 is 0. So let us draw the shells. You have 3d, then 4 is 4p, and then you have 4p. So 3d6. So if they are filled like this, so as first, as per the Hult multiplicity, all the orbitals will be filled by one electron. Then if anything is excess, then it will go by reverse direction. So now this way it is filled, this d6. And now see, if you have position number 6, you have remaining 1, 2, 3, 4, 5, 6 orbitals, right? So if ligand comes, they have to give the electrons in these empty orbitals. So this orbital will join or combine to form a hybrid orbital that is called sp3d2. Okay. Now, if you think of another way or another scenario, so you have like this, all these are paired up. Now what will happen? You have 4s, 3d, 40, 40. So now you can see from the inner orbital 3d, you have the empty shells. So your ligand can donate electrons here. In this case, you can form D2sp2. Both of the cases, this is octahedral. Both of the cases. This will be octahedral. This will also be octahedral. But there is certain differences. What is the differences? You can see this outer orbital d, outer d orbitals are used to form this hybridization. They are higher in energy. That is why these complexes which are used via outer orbital, these are called labile. Labile means reactive. And one more thing, whenever you have some unpaired electrons, it can attract, it can be attracted by magnetic field. Magnetic field. And in this behavior is called paramagnetic. If you have unpaired electrons in this situation. For the second scenario, you don't have any unpaired electrons, all are filled up. So this will not react to any external applied magnetic field. This will be called diamagnetic. And as the inner d orbital is used, this is lower in energy. So these complexes are called inert. Okay. And as they are paramagnetic, these are also called These are also called high spin, and these are called low spin. So valence bond theory could explain the shape of molecules, shape, hybridization, and all, but it could not explain then the color, from where the color is coming, and the change in magnetic field with temperature. Okay? Certain things is it could not explain. So this is why people resolve to a new theory that is called crystal field theory. So crystal field theory is different in terms of valence bond theory. So its assumptions are different, completely different from valence bond theory. So this assumes that ligands are point charges in space. Okay. Second assumption is that all interaction of metal and ligands are electrostatic. So there is no covalency involved. This was the main difference between valence bond and crystal field theory. Okay. So these electrostatic interactions, how can you differentiate between your neutral and anionic? Suppose you have neutral ligand. Okay, you don't have any charge. Say for this uh, water, you don't have any charge. You have lone pairs, but you don't have any charge. So how can you define it? So you can define it like a dipole. Okay, dipolar also have delta plus delta minus. Okay, like this. So it has a uh, sort of electrical charge, partial electrical charge generating. So this dipole can interact with metal. Okay, and for anionic, you already have the negative charge. So this can also interact with the metal subject. Now let us discuss more about it. So this is the basic thing. It will be energy. Suppose you have d orbitals of free ion. Free ion means it does not feel any repulsion, nothing. Okay, free ion in space. All of your d orbitals, 5d orbitals you have, right? dxy, dyz, dzx, and then dx square minus y square, dz square. 5d orbitals you have. All of the d orbitals will be of same energy. So this is the free ion energy level. All are same level. Now you take this d orbitals into a field or crystal field, but it is spherical. This is sorry. This is spherical. So your metal is sitting at the core, and on the sphere surface, somewhere is your ligand. Say here, here, or here. Somewhere is your ligand. So you can say on the sphere surface, anywhere your ligand will be, it will exact the same interaction. It will interact the same way with the metal, right? Because spheres are most symmetrical. Most symmetric. So on the surface, anywhere your ligand will be, it will interact the same way. So still in the spherical ligand field, you will see that all of your d orbitals will have same energy. This is free. This is in spherical field. Okay. So now, if we introduce some other uh, field which is not spherical, so then this degeneracy will be lost. Degeneracy means the energy degeneracy. Okay, same state of energy. So now say we are putting this metal in the octahedral field. Now it is not at all spherical. Then you can see your 5 orbitals are dividing into 2 set of orbitals. Okay, why is that? Why 2 are much higher and 2 are getting lower in energy? So actually this is 0.6 and this is 0.4. So these 2 orbitals, they are dz square, dx square minus y square, and these 3 are dxy, sorry, xy, dyz, and dxz. Why is that? Let us understand. So if you consider the shape of the orbitals, what is dxy? So suppose I am this one, you have y, z, and x. Okay, dxy will fit somewhere here in between the axis. Okay, dxy, dyz, dzx, these are all in between the axis. Nothing is along the axis, right? In octahedral field, actually, metal comes along the axis. This is the metal direction. This comes along the axis. This is dxy. Similar is for the dyz and dzx. Okay, in between axis. But for dz square and dx square minus y square, so dz square is like this. Suppose this is the z axis, this is y, and this is x. So z orbital look like this. It is along z axis. Okay. So if ligand is facing this way, it will experience much more repulsion from the electron cloud of the d orbital from the metal. So that is why this dz square gets high in energy, and then also dz x square minus y square is like this. Suppose this is x, this is y. It will be along the axis. That is why this orbital also faces too much repulsion, and that is why it goes higher in energy. And these 3 set of orbitals x, y, yz, and zx, they comes down from the center. This is called barycenter. Okay, so these are stabilized. If you can see, two orbitals are higher in energy. These are called EG set. These are called T2G set. EG is dz square dx square minus y square and t2j is dxy dyz and dzx. And this is the energy delta E, that is the difference between Eg and T2G set. Okay, so this is also called delta zero, and that is called crystal field stabilization energy. Okay, or CFAC. Now, as I already told you that you have a center present here. This distance between the center and Eg is 0.6. This distance is 0.4. 0.6 respect to delta O, 0.4 respect to delta O. Now, how will you calculate this CFAC? The formula for CFAC is that zero 0.6 into number of electrons in each level plus minus 0.4 into number of electrons in the T2G level. So why there is minus charge? Minus charge is coming from the stabilization of orbitals. Okay. Now, what are the factors? Factors governing delta zero value. So one is metal oxidation state. Okay. Then ligand field. Okay. So ligand field is one more thing that we need to discuss. So for metal oxidation state, if your oxidation state increased like N plus O, 3 plus state will have much higher delta O value than 2 plus, then 1 plus. Okay. And from the ligand field, we have to get to know of one thing that is called spectrochemical series. There is a order of ligands. So let me write it first, then I will tell you. So it will be like halogens at first, somewhere you have neutral ligands, you have this neutral ligands, then you have moderately strong field ligands, so you go along the way from left to right, you will see that your ligand field strength increases. There is a reason for that. Why? You can see at extreme left, it is all your halogens or the halides. So there is two things that is called sigma donation and pi acceptance. So the ions that are present in the left side, I think there is some interaction. Someone, can you mute your mic? Some mic is.
आवाज कमी मार की ओनता
Soumya, can you mute your mic? Some voice is coming. Okay, thank you. So let us continue. So you can see at the extreme left, all are halogens or halides. So these can do only sigma donation. Okay. So they have field sigma orbitals that can donate electron to metal center. Compared to this one, at the extreme right edges, you have pi acceptor ligands. So this kind of cyanide or carbonyl, you have some vacant orbitals on the carbon that can accept electrons from the metal, and this is also called back donation. And for this effect, this metal ligand bond becomes much more stable. Okay, and due to this, your ligand field increase, and then your delta zero also increase. So there is a comparison. Uh, two terms are there. One is called delta zero, that is called crystal field splitting, and another term is called P. P is called pairing energy. I'll give you an example. Say you have this complex. It is already told in the class, but still I will discuss once again. 3 minus CR H2 6 B plus CO H36 2 plus CO Cl6 3 minus. So all these complexes, chromium is in +3 oxidation state. +3 +3 +3. Okay, this one is very weak field. This is also weak field. This is moderate, and this is strong field. Let us see. Let us see for chromium. So chromium is chromium 3 plus. So for is 0 3 D 3. Okay. Then you can have like this. This is your T2G. This is EG. This is T2G. This is EG. You can feel like this either or. higher energy will be Eg and lower energy will be T2G. So you can fill it either like this way or for this one it is not possible. So just a second, I'll change this example because for D3 you cannot observe this for G4. Let's say Fe2 plus. Fe2 plus you have 4s0, 3d6. Two complexes I'm showing FeH2O6, 6, 2 plus, Fe, Cn6, 4 minus. Both of the cases, metal will have +2 oxidation state. Okay, Cn is all minus, so 6 minus 4 it is 2. Now, if you see the filling pattern, Eg, T2G, Eg, T2G. So D6, okay, 6 electrons are there. You can first go by Ohm's rule, 4, 5, and then 6, or you can go by like this. Okay, this is it contains paramagnetic, unpaired electrons. So this is called high spin. High spin. This is called low spin because it doesn't have any unpaired electrons. So H2O, it will give you weak field. Why weak field? Because it doesn't have any pi orbital. Okay, it cannot take back any electron. So as I told you here, this one, the orbital that will take the electrons will be always pi. That is why it is called pi acceptor. And the electron that will be donated, that will be sigma. So the interaction is like, say you have metal, you have a carbon and oxygen. This is a sigma. Sigma orbital is always along the bond. It is a head-on overlap. So this way electron goes from sigma, and then you have this pi. This is pi of your carbonyl, this is pi of metal, this is field. So from there electron goes to the empty orbital of carbon. This is called the pi interaction, pi acceptance. Okay, this is how it goes. Now, due to this, the bond becomes stable. This is called strong field, and you get this configuration where all the electrons are paired. So for strong ligand field, your delta 0 is much higher. Here delta 0 is small. So I told you there is one more term that is called pairing energy. So you can see when electron gets paired in one orbital, if two electrons are there, it will have repulsion, right? Always it will have repulsion. So two unpaired electron always has repulsion. To overcome this repulsion, we have to give one energy to overcome electron repulsion in same shell. That is called pairing energy. So when this delta 0, there is always a competition between delta 0 and P, pairing energy. So when delta 0 is small than P, then obviously system will go towards this. So delta 0 small means this gap is small. So electron can jump from here to here easily. When this gap is large, so it cannot jump. So what it will do? It will come back to the same shell and it will pair up. So in that case, so here your delta 0 is small compared to P. Here delta 0 is very large compared to P. This is the case. Okay. And these things, this variable, so one more term is there. We don't know. This whatever low spin and high spin, it is called spin state. Okay. Low spin, it can be, or high spin. This is observed for D4 to D7. D4 to D7 case. Okay. At weak field, it will go to high speed, as your delta 0 will be very much smaller compared to P, and at high field it will be low spin because delta 0 will be higher. Okay, as you can see it here, delta 0 is higher, it cannot overcome this much gap. It cannot go from T to G ground level to the excited level EG. So it will gradually pair it up. Okay, and this phenomenon is called spin crossover. Very important topic. You can study on your own. This is advanced research topic. This is called spin crossover. Okay. Then okay, some more effects, some more factors. Factors of delta 0 is that if you go down the period, sorry, down the group, your splitting increases. Suppose you are going from cobalt to rhodium to iridium. So all these have similar electron configuration, but this is 3D, this is 4D, this is 5D. So as delta 0 increases, so this delta 0 is somewhat comparable to P, this delta 0 is greater than P, this delta 0 is much more greater than P. So in these cases, always it will be low spin. So that is why we tell that the spin crossover, sorry, the spin crossover is a phenomenon of 3D metals, because all the other periods 3D, 4D, 5D, they all show only low spin state. Okay. Then small part is left. So this was all about octahedra. For tetrahedral cases, you see you have no longer 6 atoms, you have 6 ligands, you have 4 number of ligands. And thing is that if you have less number of ligands, your repulsion is less. And one more thing, so how can you construct tetrahedral? Is like that you draw a cube, draw it like this way. draw a cube, and then all the alternate corners you put one atom, and center is your metal. Yeah, metal. Now if you connect it, if you connect all the points, you will get one tetrahedron. So what you can see from here is that you have X along here, Y along here, and Z along here. Any of the ligands are not along the axis. So they are all in between the axis, right? Because of that, so let me rewrite this. There are 2 points. One is number of ligand is less 4, and second point is ligands are not along the axis. So that is why repulsion is less. Okay, that is why repulsion is less. So this delta T, that is the CFS for tetrahedral, is always very low. Okay, and what we can think of is that it is always lower compared to any other geometry, right? And you can consider it like this way. So as these are always in between the axis, so here we don't use the G term. G comes for the inversion center. That is present for octahedra but not for tetrahedra. So only write this term T2 and E. So for tetrahedra, this angle will be always okay, 109 degree 28 minutes. Then if you have two sets of orbitals, one is T2 and E you have two. So do you know how this T2 and E comes? This comes from the group theory, but you don't have to study right now. You can study in some advanced studies, advanced courses. So T2 means strictly degenerate, that is why you have three orbital. E means doubly degenerate, you have two orbital. So now E means you have two, then you can divide this angle and it means by 2, then you will have 54 into 3, 44 minutes. For T2, what you will have 109 into by 2, you will have 35 till 16 minutes. So these angles tells us how much close to your nucleus or the metal center your ligand is. So for T2, it's closer to metal center compared to E. So that is why T2 will face more repulsion, and more repulsion means more energy, right? Then let us see what the energy will look like. Suppose this is your spherical field, then you have 3 here, and then only 2 here. So one thing you can notice that this is called delta T. One thing you can notice is that none of the sets are stabilized, all are destabilized. Okay. So this was not the previous case. And in comparison to the previous case, this is much more smaller in energy. So this one comes at 4/9 fraction compared to, and then down. Okay, why is that a factor 4/9? So there is two part. So 2/3 comes from 4 ligand instead of 6. And then another 2/3 comes from the less repulsion due to the geometry. Okay. So typical values for this complexes will be, say for this one, 2 minus 2 is 3300 centimeter inverse. It's 2900 centimeter inverse. And then if you have some strong field ligand also, comes in the range of 9000 centimeter inverse. So you can see even with a strong field ligand, your splitting is much less because of the geometry, and that is why always you will have spin complexes. So let me tell you, for this package, for low spin octahedral, the splitting should be more than 30,000 centimeter inverse. And if you have a moderate case, it is somewhere between 10,000 to 30,000 centimeter inverse. And if it is less than that, it will surely going to be high spin. Okay. So I think there is one part that is just started, but I will not discuss it much more now. That is called spinel. So this is a special type of structures represented by this formula. It is called Ab2O4. So this A and B are metal ions. Okay. Sitting in octahedral or tetrahedral cavities. Or more appropriate term will be void. Okay. So according to that, where it is present inside the lattice, so it can be normal or inverse. So all these things will be covered in week 3. So maybe next lecture we'll discuss all of this. And now let us solve some of the questions. Yeah, so I have shown some of the previous year questions here so that we can have some idea apart from the general discussion we had. So this is the first question. The total number of geometrical isomers for the complex ion, that is cobalt H2O2 and ethylene diamine PrCl. So this is having, so let us first see what is the total number, coordination number. So H2O will be monodentate, ethylene diamine will be this one, this is two bidentate, and this all will be one and one. So all combining all the coordination number will be 6. So this is hexa coordinated. Related. So most probably the geometry will be octahedral. Okay. So do you have any idea how many geometrical isomers will be there? So let me draw the complex for you. Okay, so this will be the complex like this. Any idea how many geometrical isomers it will show? Any idea? So this will actually have 4 geometrical isomers. So this OH with respect to each position. So you can have this one, then you can have, so actually this 3 dimensional structure is like this. Just for representation, I'm showing like this. So one will be like this. This is what. Then we'll have this one and the other one. Okay. So as ethylene diamine is only chelating ligand, so it will form a cis around like cis type addition around the cobalt center. and then according to the relative position of the uh, water molecules, so you can have different organizations. So you can have cis one, two, and three ways, and you have trans in one way. Okay, according to the relative positions of bromine, bromide and Cl also. Altogether, it will have four. Then is the right answer. We go to the next one. So this question is, which one of the following complexes can exhibit geometrical isomer? This is a similar kind of question. Okay. So one thing is that in these tetrahedral complexes, geometrical isomerism they cannot show. So we have left with the option for square planar. So let us draw it. We have two water. So this is one form which is called cis, and you can also have one form H2O, H2, HCl, Cl. This can be considered as the trans. Okay. So this one can exhibit geometrical isomerism. Apart from that, if you see in square planar, you have this complex copper H2 one. So all the ligands are same, you cannot do any differentiation. And then you have octahedral, but here also you will have the same molecules all over. So in this case also, whatever place you assign to this chloride ion, it will be the same isomer. Okay. So this cannot show any geometric isomer, only one can show. This is the right answer. Then the next question is, among this following, which one is paramagnetic? So let us see cobalt H2 6 3 plus. This is cobalt 3 plus. Cobalt 3 plus moves towards 0 through to 6. Okay. And for ammonia, ammonia is a moderate field ligand, but for cobalt 3, it will act as a strong field, so it will be cobalt 2 low spin state. It will be like this. Okay, this way. It will not have any unpaired electrons, so it will be low spin. Let's see for B, what is the case? Anion will go to minus. So you can see it is 4, that is tetrahedral, and for tetrahedral, all of the cases it will be high spin. So we can uh, we, we see that it is high spin means it is paramagnetic, and it will be your right answer. So we don't need to look for another options because already we found one. This is the last question. So it says the total number of geometrical isomers for the complex I here H2O2 here here here. So can anybody tell what will be the answer for this one? I think this is similar to the first question that we have discussed. Yeah, this will be the same. This will be exactly same. So instead of cobalt, you just have iridium here, and then you have H2O, and you have ethylene diamine, and here, and Cl. So as you can see from the previous questions, the correct answer will be 4. So 4 ways it can form the isomers. Okay, so that's all from today. So we can meet on next class for the week 3. And if you have any questions, you can reach out to me, or you can write in the discussion forum. We can check and we can answer. So thank you all, and all the best.